hear me? All right, can you hear me well? Okay. I think this is good because I can walk and show that I can walk, and when I get tired, I can sit there. So thank you very much. Okay, I shouldn't kill myself here. Thank you very much. I appreciate you. Appreciate you being here. Thank you very much for inviting me here. Where do I point this? Oh, you do that one, okay. I don't do anything. So this is a toy. I just keep around with it. Okay, all right. Thank you very much, Vice Chancellor Professor Ramesh Varma. It's a pleasure because we were roommates 1964 and 1966. We are just kids. We are babies. And I never thought I would be here, invited by him, and be in front of you. Thank you. And appreciate Dr. Parvati because without her, this would not have been possible. I was planning to talk online. You know how bad it's going to be because now I'm in front of you, and thank you. And without her, this would not have been possible. And before I start, I may be looking at here, and I start my watch to make sure that I don't exceed more than an hour. So I'm going to keep my watch looking at it because I know it is not polite, but I hope that you won't mind that one. Right now, I feel like an Uber driver. Why? Because when I get to Uber, you get out of it, he will say, can you give me a 5-star rating? So I'm going to ask you, can you give me a 5-star rating? What do you think? Up or down? Okay, you don't know yet. Let's wait and see. Next. My narrative is going to be in 3 parts. Part 1 is that I have taken chances. So did Dr. Ramesh Varma. We took chances. Without taking chances, you cannot get anywhere. Second thing is that I'm going to give my experience, my success and failures. In fact, most people have more failures than success. And failure is a template of learning. So never be afraid of failures because that's how you learn. Next, then I'll transfer that my experience coupled with some of the amazing products which in my lifetime I have seen, 1 or 2, and give you some idea of the basics of successful innovation. Now, there is a secret recipe, and I'll share that with who is sitting just in front of you, not the faculty, but just the students. And I do want to talk about rethinking education schools and colleges because as I learn more about this institution, I think it's an amazing institution. You have a great place. You're getting good education. But my experience lately has been in Kerala where I live or not stay for about 4 months in a year. And I have some issues and I'm concerned about education because that's a building block. Without it, I won't be here and you will not get where you need to get there. And my closing remarks and some questions and answers. Thank you. Next one. Right, I did my PhD in the influence from NCL, National Chemical Laboratory, Pune. And my PhD was an accident. Like many things in our life is an accident. So I came to Bombay in 1971. It was Bombay, not Mumbai. And I went for an interview at Fertilizer Corporation of India for a purchasing officer job. The interesting thing about that, I didn't know anything about Fertilizer Corporation of India. I have no idea who was a purchasing officer, but I went there. I have an MSc degree in physics. When I went there, I had an interview. They were talking in Bombay Hindi, which I didn't learn it because I haven't watched enough Bollywood movies at that time. And they were talking, and I got bits and pieces of it. Part of that, wo to bechara hai? I said, yes, sir. Was a pereshan here? Yes, sir. They were talking not to me, but my yes, sir, gave me the job. They said, you're getting the job. And I think, so what did give me the job? Was I bechara or pereshan or yes, sir? All of the above. All of the above. and on my way back, I got down at NCL, and not NCL, Pune, and my father was with me, and he took me to his nephew, took me to NCL. When I got to NCL, my God, what a building! I never seen that. I never seen an air-conditioned building. I never seen a flower bed, walk bed go towards the lab, and everyone, all chemists walking around in lab coats and test tubes in their hand. I thought, yep, this is it. And, and I met a physics professor there, my guide. He gave me a JR of Junior Research Fellowship, 300 rupees. Out of that, I sent 75 rupees home, and I saw 3 movies per month. So that's what I did with it. And so I did in vacuum technology. Well, vacuum technology is, I didn't know much about it, but it's fun. It's evaporating metals like gold, aluminum, zinc onto a substrate. And it's a technique that you can transport a solid to a different element or different surface, transporting it in atomic form. But if you use a compound, for example, silicon nitride, silicon carbide, gallium arsenide, you cannot do it because they dissociate it. So what do? You can do chemical vapor deposition, CVD, in which case you take the gaseous form of chemicals and crack them pyrolytic, either using temperature or field, electric field, or both, and then let it combine and you can form. That's how you form silicon nitride, gallium arsenide, indium phosphide, or similar materials. And the third technique is molecular beam epitaxy. You use a beam of molecules to form what you want to form. Why do you want to form? That's how you form controlled materials. Controlled materials are needed to make particularly semiconductor products, such chips used in a mobile phone. So I enjoyed it, but I got good at fixing things. And I was very good at fixing pumps because nobody else was there. It's a dirty job, so I did it. So I did my dirty job. I got my PhD as well in the process. Then I moved to postdoctoral work in UK, and I had a chance to work with Sir Robin Williams. He was a reader then. He became a Sir or knighted about 10 years ago. I'm still friends with him. And there I worked on surface physics, which is a new area of science for me. But we won't be talking about that today because I want to confine my talk to small aspect of physics and what I did with it and move on to success or failures so that we can learn about what we need to do, what you need to plan for a general audience. So it would be, but one thing I was doing, I was always thinking about what can I do with what I learned, not just for myself, to making a product or do something with it. I played around a lot. Most of it didn't work, but some of them worked. Next one. Here's my picture. That's Robin Williams and me. Well, that's still me. I know you won't believe it. That was 1976. Next one. From there, in 4 years or 8 years later, I moved to AT&T Bell Labs. And that was a chance. Again, I was talking to you about taking chances from Fertilizer Corporation to NCL to UK to Bell Laboratories in New Jersey. So no pain, no gain. You have to take chances. Calculate the chances. Don't take unnecessary risk. But if you don't take any risk, you will not get anywhere. So I was lucky because my department head was Arno Penzias. He was a Nobel laureate. There were 12 Nobel Prize winners in the department. And I was working in the lab. Well, Bardeen, Bratton, and Shockley, they invented the transistor. The first transistor was invented in 1947. Two big things happened in 1947. India got freedom. India was free after 300 plus years or even more. And the transistor was invented. The first transistor was germanium. but it became more into silicon technology. But the United States didn't know what to do with it and gave to Japan the technology after Second World War. Guess what? Japan was, the Sony Corporation was primarily making pressure cookers, rice cookers. And they got this patent and they played with it. They built the first transistor radio. Think about it. They made the first transistor radio. And Willard and George were my, not the office mates, the next lab, and they got Nobel Prize in physics, charge coupled devices, CCD. Nice experience, lots of chances, and of course, lots of luck. Next. No, I'm good. Work here. Okay. Mail, oh, no. Mail like how do you go backwards? Okay. Okay. This is backwards. All right. Okay. Now you know how to go backwards and forwards. Okay, let's talk about three types of materials: metals, semiconductors, and insulators. We physicists want to learn those. We'll have to make in a piece of paper look like, you know, it's a diagram, because we like diagrams. One way of learning about this material is energy band diagram. What is an energy band diagram? It's a graphical representative of energies of electrons. You know atoms, you know electrons and different shells. They have different energies. The one at the top has highest energy, the one at the bottom, the case, has low energy, right? So how do we represent it? We represent in a graphical form the filled band, where you have electrons filled it, and then the unfilled band, which is no electron. If you apply voltage, you can take the electron from the bottom, from the valence band into the conduction band. What do you get when you apply voltage? When this electron moves, electric current, right? So in a metal, there's no gap, collapse. The valence band and conduction band are collapsed. So when you apply voltage, immediately you get a current. In an insulator, they are separated, there's a gap. So what happens, there's a gap? No electron transport, no current. So that's why they're called insulators. And there is something in between. You apply a small voltage, you can get the current. So you can control the current using a small voltage. In a metal like a copper wire, you cannot control it. You apply, boom, immediately the electric current flows, correct? But this controlled electric or electron path, that's what is important to make products out of it. So now let's go into 3-5 semiconductors. What's 3-5? I believe you must be familiar with periodic tables. Group 3, group the gallium, indium. Group 5, phosphorus and arsenic. And these are called direct band gap materials. And there are indirect band gap materials, which is silicon. So I'm going to talk a little bit more about direct band gap, because that's what work I did it, and that's the application, what I will be talking about it. Okay, it's the same thing again, slightly different band diagram. Is there a laser pointer here? Oh, no. Oh, mail, okay. All right, there you go. That helps. But this is a laser, so I'm going to get back to you, the work we did to get to this laser here. So, okay, this is good. So this is a band diagram, and here's energy, and this is the momentum of electrons. Right? So that's why we put energy and momentum, and the one here is the valence band, and it's a conduction band. And when you apply voltage, there's electrons here, and when the electron moves out of the valence band, what you get? A vacancy. So the circles here holes and these electrons. When you apply voltage, what happens? The electron falls and combines with the hole. Well, the electron and hole combine. What do you get? Energy is released because there's a lot of energy. It can come out in two forms, photons or phonons. Photons is light, phonon is just heat. But in this particular case, the direct band gap material, you get light coming out of it. Oops. So I screwed up. Okay, there you go. So the electron and the holes combine, you get H nu, then the light comes out of it. And that's called recombination. Now, once the light comes out of it, what does this light do? If the light goes and hit a stimulated atom, and the electron can absorb it and fall from the high energy state, low energy state. Let's say from Mn state, N state to K. What the difference in the energy, it comes out of light again. That's called stimulated emission. So recombination means electron and hole recombine. You get light. That light goes and hit another electron at a high energy state. It absorbs it, falls down to lower level, and second layer of light comes out of it. So that's called stimulated emission, and that is exactly what laser, that's how laser functions, stimulated emission. Laser stands for light amplification by stimulated emission of radiation. Okay, this is a typical of a laser. This is a gallium arsenide laser, and it is used in fiber optics and transmissions and cable TV, and I will talk a little bit about it. Its application in laser printers, scanners, and this also. Yeah, this is the red laser, right? That's in the red wavelength. And the one we use in transmission, for example, in TV transmissions through broadband, it is in the 1550 nanometer wavelength. It's an infrared. So 1550 nanometer infrared red is about 680 nanometers. So nanometer or 1500 nanometer is 1.5 micron. And this is laser. How do you make a laser here? It's a gallium arsenide substrate, and it is a cleave. There are two mirrors, and this is the optical waveguide. It's a cavity. The cavity is 1 micron. What's a 1 micron? So human hair, not mine, I don't have any, your hair, it's somewhere about 75 microns. So give an idea of the optical cavity is 75 times thinner than a human hair. So a typical laser dimension is about 0.5 millimeter width, 0.1 millimeter thickness, and probably about 1.5 to 2 millimeter in length. They're very, very tiny. So how does it work? So you can confine the material gallium arsenide between two cladding layers. And the cladding layer, two refractive index, different refractive index. What happens refractive index in a glass? You send light through, it stays inside, right? Total internal reflection, light. It doesn't come out of it. So here, the light doesn't come out of it because it's confined. So light stays inside in a cavity, like a tube. And now it's amplification, stimulated emission. What has happened? It goes. The amount of light goes up and up and up. Intensity goes up. Frequency or wavelength is still the same thing, 1.5 micron, for example. And after a while, it cannot stay in the cavity anymore. It jumps out of it. When it jumps out of it, it comes out of it, and it's called facet. That's where the laser light comes out of it. That's what this laser light comes out of it. See, now you got an idea, right? What the laser is like. So I'm going to recap it. I'm going to ask questions, all right? So we talked about various methods of deposition, right? Vacuum deposition, chemical vapor deposition, and molecular beam epitaxy. Next is the three types of material: metals, semiconductors, and insulators. And I did pick up gallium arsenide, even though that 95% industry in the world now is using silicon, because integrated circuits, silicon chip, they're all 95%. But the 5% around used in the gallium arsenide or indium phosphide. Because why we use it for lasers? Because it's direct band gap. Because remember the picture I showed you, there's a minima and a maxima. It lines up. So when there's electron transport, there is no momentum transport. Because you don't, it's exactly right at the position. There's no momentum change. And that's why there's a direct transition, recombination, and stimulated emission. And we talked about semiconductor lasers. So that's my recap. Right, now I'm going to applications that, less physics, but hopefully you can relate to. Um, this is the fiber optic cable called undersea cable, and I worked on undersea cable from 1982 Type 8 in England, and I ended up finishing that in 1987 in United States. Type 8 is the very first optical amplifier in the world, and also it placed under the Atlantic Ocean from New Jersey to England to France. So three telecommunication companies decided to join together, and they were AT&T, company I worked, British Telecom, and French Telecom. So this fiber is kept somewhere around 4 kilometer, 11 kilometer. That's the depth of the water in Atlantic Ocean. Somewhere around the deep is 11 kilometers. And they're repeated, that means the signal is always lost. You need to amplify the signal, right? You cannot send one signal from the other end of the world without amplification. In between is called amplifiers, called repeaters, they're amplifiers. And they're about 40 kilometers apart. And the longest one is 45,000 kilometers. That's around Africa. They call ring around Africa. 45,000 kilometers is the longest fiber optic cable. And the cable laying speed, that is the interesting thing, that it's from a ship which basically just throw it out into the water. That's not what you can do. No scientists, engineers, they're mostly seamen. They are captains and seamen, marine. They take the cable with, not by hand, because the amplifier is about 1.5 tons, so you cannot carry it. So machine takes it and just dumps into the water. And this is how it lies down at the bottom of the sea. And the ship is traveling at a pretty decent speed. That's about 12 kilometers per hour. So basically the fiber and the amplifiers are dropped and the ship is running. Now, hopefully this will excite you. There are 15 cables coming to India, and there are 5 landing stations, 2 in Kerala, Kochi and Trivandrum, Chennai, Tuticorin. There's one in Mumbai. So you do have. So though you may not be aware of it, you are making a phone call to America, you are sending a message, or you are on a Facebook looking at it, or you are WhatsApping to somebody else, all going through the fiber optic cables. And who are using it? These are the customers: Tata, Airtel, Global Cloud, that's Reliance. I hope you can see it. And I worked on 3 of these projects: CMEV3, Flag, and Falcon. So I worked about 16 to 18 years, and I had an opportunity to work on 3 of the projects. And I know that I'm pleased to see that 3 of them is touching the country of my birth. Interesting, the TATAs were installed in 1988. At that time, we thought that it's a 280 megabits. Now it's into almost gigabit. There's 40,000 circuits. It will take about 6 years saturation. 18 months, the project, it is oversaturated. There's no opportunity to expand it. And what happened, it was taken out of service in 1992, because that quickly, the need of the bandwidth grew that much faster. And now we live in a world, all of you, all of you you're using so many bandwidths. Where does it come from, the bandwidth? All come from compressing the signals and sending it through cable, or now you can also do satellite. So that's what bandwidth, compress it, send it. Another work I did was I moved from 3,5 gallium arsenide indium phosphide to silicon carbide. It's a high temperature material. High temperature means that the electrons mobility will not go down as you increase the temperature. One of the reasons our devices fail because the electron scattering, just scatters around. Mobility means that the distance traveled between point A and point B, scattering. The longer the mobility electron can transpose, it can do things. Shorter means that it is losing energy very quickly. So most of the materials like silicon, even gallium arsenide at some end, it does lose and it loses its mobility. But silicon carbide is a material which is a high band gap material. It can work at high temperature. It can work in 80 to 90 degrees Celsius, whereas silicon can work maybe about 40 degrees Celsius. After that, the functionality goes down. And my work was working on the building silicon carbide transistor, and this is an array. What's an array? The array is a radar built, and the radar probably is about 40 meters in width sometimes. It's big. There are thousands and thousands of transmitters or lasers inside. And this is built by Lockheed Martin, and they build the aircraft and then the missiles attached to it. Northrop Grumman, we built the array, which is active electronically scanned array, means that continuously scanning. Do you know there's an office of Northrop Grumman in Delhi, mostly to work with the Defense Department? What does it do? It can scan continuously, look at aircrafts, enemy aircrafts coming. It can also scan what's happening at the ground. Continuously it can scan it. So it can do all the operations in one shot. Well, to compare, right? It's always good to compare. F-35 is a stealth aircraft. What's a stealth aircraft? Means in a stealth mode. Stealth mode means that you cannot notice it. So when the stealth aircraft goes, it's difficult to detect. How do you detect? Using a source of energy and reflection, right? You reflect it, mostly microwaves. You send a signal, look at the reflected back, and you image it. And that's how you look at whatever is up. But if the reflection is damped, in other words, that the light, the signal is absorbed from the surface of the body of this aircraft, then you can see it there. That's what stealth mode. And comparison, we have to compare with Rafale. That's made in France. Both are about the same, similar performances. And India about 36, Rafale, and Google. I lost money on that one because I didn't buy any of this F-35s. That's okay. And 36 or 35 of them are being delivered. There's one probably this month. So good thing for Indian defense system because I think Rafale is very good, equally good. Now, I want to move to failure and reliability. Why do I want to talk about failures? Because almost everything fails. Some point in time, everything fails. So if you want to design something, you're working on something, you think, well, it's going to work. No, we are in trouble. Everything fails. So if you know that things are going to fail, you can do something about it. If you think that, well, there is no failure, I'm going to do it right, no one ever does it right. If anybody told you, even your parents, I did it right, absolutely not. I'm a grandparent. I never did things right. So. And the reliability, what is reliability? Means that you buy something, you keep it forever, like, Apple computer, your vice chancellor using an Apple computer. I have a, non-Apple computer. His lasts forever and mine just fails every maybe 4 or 5 years. But he pays more money for it. So what do we do? Before something fails, we need to predict, we need to understand it's going to fail. So how do you make something fail? Accelerated testing. What is accelerated testing? Take it to the extreme level. Let's say you have a mobile phone. You are using it, let's say 10 degree or 0 degrees Celsius to 40 degrees Celsius. So if I have to develop it, typical standard testing is minus 40 degrees Celsius to 120 degrees Celsius. So you take it to extreme, temperature cycle it up and down, 1,000 to 2,000 to 10,000 cycles, up and down fast. See when it fails. The other is that you take to maximum rating. You shock test vibration. You know what is the most common mode of failure of mobile phones? Number one is that you cannot find it. Number two is the drop test, that it falls. In one particular direction it falls, it breaks. If you drop it fast, it doesn't. But if you go in the corner, it breaks. And that's because of axial failure. Because this is a mechanical failures, that it is directional. That means X, Y, and Z. One particular direction, the fracture, its propagation is faster. Maybe another time we can talk about fracture propagation. So what are the root causes of failures? Why things fail? Well, some of them are defects in materials because of what you purchased. You say, for example, your mechanical parts, there's a defect in it, and your semiconductor parts, there's a defect in it, or the wires you put in, there's a defect in it. And the next one is product design without specification. What's a specification? How does it matter? For example, I'm asking you to build a car. Do you really go and build a car? Where do you start? The question number one you're going to ask me is that, well, what's your specification? How many people should travel? How many miles you should get per gallon? And what the road condition? Is it going to be in a nice road? Or this going to be like in Kochi where I live, just ups and downs? And the other environmental requirements, where is it? To give an example of environmental I believe somewhere in the 50s or 60s, there's some product was transferred from England to India to build. And in the requirements it is written room temperature. You have to build it or test it room temperature. So that is the requirement. Room temperature in England is way different than room temperature in New Delhi. So that was the root cause of failure. That's the requirement is very important. You cannot just write room temperature or I want this function. What do you want? It's absolutely critical that if you do anything, ask what you really want. Ask the customer, what do you want? Sometimes they don't know what they want. You have to help them what they want. And of course, it always happens in a team, in a faculty, student union, department, council, parliament. You disagree, constant disagreements, and there are personalities. Some you can handle, some you cannot handle it. And most of the projects I know fail because inadequate funding, because it's not enough, because we could not estimate exactly what is the cost of it. So the money, I know there's some here who are in the finance or management. Well, talk to them. It's an important thing that money, how much money? Can't expect engineers, scientists, even worse. We think that somebody is going to feed the money all the time. Why? Question I would ask is that, do you put money in your pocket? So when I do a project, I ask myself, do I have faith in it? Am I going to put my money in it? If I don't put my money in it, why would somebody else put their money into it? Good question to ask, correct? And the leadership is always the case, right? Now coming back to basics of successful innovations. So, so my experience plus others' experience, leadership and team building, that is a difficult thing. And I heard that Heidi talking about that Vice Chancellor here brought some leadership. This conference here or people like me coming and have an opportunity that I have an opportunity to see you, you have an opportunity to see me, ask questions. Doesn't happen. Do you think it's easy? Get all of you from your class or you're having fun or looking at your Facebook to here and sitting here? A lot of work. A lot of work. Leadership is needed. That's one thing, leadership. Team building, you need a team. You can't do it yourself. Don't ever think that I'm going to do it all by myself, right? No, you can't do that. You need a good team. And you need to have a good relationship with your customers. Because if you fight with the customer, what are you going to get? Nothing. And we talked about requirements, testing and verification. You cannot test only at the last minute. Say, for example, you're building a car. Do you make the car and finally take it to Sahara Desert and run it? No. You have to test it at various stages of this car, right? You know, the transmission, the brakes, the safety features, the steering, the tire, the shape of it, all need to be tested at different stages, and then you do the final testing. And the financial control, coming back to money again, please, young engineers or scientists who want to be, always think about the money, because you cannot ignore money. Money doesn't come free. You have to beg, borrow, or steal. It doesn't come free. And blame games, blame is always be blaming. Oh, it's not me, it is him. Oh, it is her. No, it is them. I'm free. That's what we blame. That's the worst thing. The projects fail because we keep talking, and that's one of the problems in implementing any decent solutions all over the world. I mean, America has equal problems as much as India. We blame each other, we don't get things done. Of course, it happens here too. And Murphy's Law. Anyone heard about Murphy's Law? Anybody else? Yes? Okay, good. Murphy's Laws means that if something is going to fail, it is going to fail. Right. So it means that almost everything is going to fail. Well, if you know that something is going to fail, don't be over optimistic about it. I would say in straight language, don't be too cocky about it. You anticipate failures and then do some corrective action, proactive. Okay, now coming to secrets of success. Okay, what are the secrets of success? Taking chances and risk. No pain, no gain, right? You have to take chance. Not any chance. And of course, you need really lucky, but you have to take chances. Next is the lessons learned from success and failures. I would say that learn more from failure. There are more failures than successes. In pharmaceutical company, every 100 researchers, I know the chemistry vice chancellor would talk about it. Every 100 project, only 7 to 10 come to light. Only 7 to 10% success. That's very low, right? But lots of failures. Those who succeed learn from the failures. One of the most brilliant things happened in the last 3 years or is that the mRNA, the vaccine development. I'm sure somebody has talked about it. If not, I'm sure you'll be able to get enough people to talk about it. That is amazing how quickly, of course, a lot of money being spent. So it's a miracle, mRNA. And we need to work without expecting immediate reward. That's the problem, right? We always want reward immediately. I know that a lot of young engineers join where I work that in 6 months they want to become a manager. Think about it. I mean, I don't remember I have a chair to sit in my lab in the first 7 years, right? Did you ever sit anywhere? You were standing, my goodness. You were standing. Now, first thing is that in our lab, new engineer comes. Where is my desk? Where is my room? No, we ain't got any room. Okay, where's my desk? Okay, here's my desk. Where are my computers? Personal computer, company computer, personal mobile phone, the company mobile phone, all of that one. But don't expect things. Things will come through. Well, I didn't say that. Lord Krishna gave the advice to Arjuna. Hey Arjun, karma karo, phal ki ichha mat karo. You don't know what you're going to get. आपको ये तो मालूम नहीं है. काम करना है, आपका काम कर्म करना है. Don't worry about the result. वो तो आ जाएगा. Right? Now, ideal designs are manufactured that I have some thoughts. I don't think I have done anything ideal. So I'm going to show you something which you can all reflect on. Steve Jobs' iPhone. To me, is an amazing the way he brought it up. I don't think I can tell you all the stories, but I'll tell you one or two stories. An example of risk-taking. Elon Musk, Tesla and SpaceX. I mean, it's incredible what he did. It's completely risky. Tesla, because electric cars, and no one at the time thinking about there's going to be electric cars in the United States for sure. And the SpaceX, taking somebody from Earth to the space, competing with NASA and Boeing, impossible. He took a risk, SpaceX. Well, I'm not just confining myself to high technologies. Look at Adani Group and Reliance Group. What they have done, amazing things, right? You don't have to do fancy high-tech stuff. You can still do amazing things without doing incredible, like you don't need to get recognition from the world. You need to get recognition from people around you, within your country, and the rest of things going to happen to you. These are traditional industries, the Adani Group, power plant, food processing, coal mining. Reliance, infrastructure, finance, health, network, mobile phones. I know there are some issues going with the Adani Group, and maybe you're watching or finance people are looking at it. It's called the Hindenburg Group, the Hindenburg Foundation. It's a short-selling company. Do you know what short-selling is? All right, okay, short-selling, all right. Did you short-sell? Adani Group, did you short-sell it? All right, okay, all right, okay. That means they took a bet on it. I think there may be some truth, I don't know. I'm not arguing about it. But that's what happened, the Hindenburg. So these are ideal manufacturing. And I'm going to show you something very interesting. I hope you can see it. This is the drawing from iPhone manufacturing. 1977, they marketed it. This is the drawing. This is the exact drawing, what they have to make it, physical drawing, dimensions, materials, functionality. It's got the drawing. And this is the conceptual drawing. Look at the conceptual drawing of iPhone. And I want to compare this conceptual drawing with somebody else's drawing, Michelangelo. It's exactly what he did it. Before he did a sculpture or a painting, he did a conceptual drawings of how it looks like it. Steve Jobs and team decided that, yes, we need a concept. And I remember from one of the TED Talks in what Steve Jobs did it, he had a team of people. A team of people included scientists, physics, chemists, not kosher, but chemists, physics, engineer, mechanical engineering, electrical engineering, and artists. Why on earth you bring an artist to build a phone or something? Have you thought about it? I never did it. I never thought about it. But artists, that's called multidimensional, using resources outside it. Right? Don't ever think that, I know that physicists, engineers do have a feeling that others people don't know anything. I was one of them. Not anymore, because some of the artist's concept bring into it, enhance my own thoughts. And that's exactly what he did. This is an artistic impression of what the product should be. But the physics, mechanical, electrical engineer, they designed everything. If it left to them, it would have been like looking like a brick. So artists brought it up. And one of the other Steve Jobs asked them to do was that, I want you build a product with my customer will never keep it down. They always hold it there, right? Have you seen those who use mobile phones, iPhones, like my friend, he sleeps holding it down like this one. Steve Jobs did it to him, right? Because it's such a beautiful, my wife did the same thing too. She uses an Apple phone, iPhone, she sleeps with holding like that. Right? I wish she did holding my hand. Nope. She did the damn mobile phone, So that's what, so in a team, bring other resources. Don't confine to just your own circle. And I think there's a good institution here. I like it. The engineers, the scientists, the musicians, they all work together. In harmony, you can do good things. In isolation, you cannot do anything. Yes, you can do the worst thing. So in harmony, you can do things. Now I'm switching to a very different topic. It's important because education is important. I'm going to talk most about Kerala, what's happening in Kerala. Maybe it is happening elsewhere, I don't know. So if things are good here, I'm happy with it. But this is where I grew up and I have a little problem with it. I don't know whether you can see this one. 2 days ago, on 8th of February, I saw this in Hindu as an advertisement. That's 6 pages of it. And my wife asked me, what is this? And I said, I don't know what it is. Look at it. And it's the International Education Fair. And you cannot see it here. I'm sorry about that. It is our collector of Ernakulam, an IAS officer, a government officer. I think he was doing it, trying to sell our kids to other countries. That's basically what it is, right? So I'm going to ask you, what is wrong with our education? Right? Well, you're all educators. I want you to think about it. Here is some information I picked up in the last 2 days very quickly. There's 1.8 million Indian students are abroad right now. 1.8 million. They spend $85 billion, which is equal to 7 lakh crores of rupees. In perspective, what is that much amount of money? 18% of India's budget of 2021. We spent almost 20% of the money equal to the entire budget of this nation on sending kids abroad. Right? Now bring back to your own state, which is 35% more than the Maharashtra state budget. I think Maharashtra state, because of the industries and infrastructure around, is one of the most, the budget, highest budget. So 85 billion, the kids spending outside India, 35% more than Maharashtra. Think about that. That's not a small potatoes. Now, big question is that, why are they going abroad? I mean, they're not fools, stupid. Why are they going abroad? Mostly for marketable education, right? Is the real marketable, perceived marketable? It doesn't matter. It is marketable for the individuals. So, your institution here, all of you, I think it's a very good institution. And you have universities, you have colleges, most importantly schools, and you have an excellent opportunity here. You need to continue, the administrators, the board of directors, the faculty, continue focusing on providing quality education. It's debatable what's quality education. I was talking to Vice Chancellor earlier today, said that I grew up in a village. There was no electricity till I was 6 or 13 or something. And my school, there was no desk. I sat on the floor. But I had amazing teachers. They totally one of few things, a little bit of English, a little bit of Malayalam. Didn't learn Hindi at that time. And if I wish, I would have understood that my first interview, right? If I understood it, I didn't. I still got the job. And but high school, college, unknown colleges I went. But there are teachers that are teaching me something really basic, fundamental. Didn't teach me a lot about it. So what's happening is called depth. The knowledge has two things, depth and breadth. Ideally, you want to have breadth and depth. So I'm borrowing the word from Vice Chancellor here. That depth. Your only job as a teacher is show the door, right? Get some good knowledge about something. Don't have to know everything, But now the education, at least in the United States, I find it broad. Too many things. Too shallow. That's what's happening that some of the engineers, they know a lot of stuff. They don't know anything. So my hope is that I'm not advocating against breadth. I'm advocating for depth. In the United States, now the employees, even the company I work, we don't look at the degrees, okay, it's great, but we ask questions. See, can you solve problems? And can you adapt yourself? Because technology is changing. So your skill, degree is important, but more than the degree, what you can do. But how does it, so you're hiring me. How does it matter what degree I got? You want me to do something what you want me to do, right? So the key is that get passionate about something. Don't worry too much about your degree or fancy degrees. Be passionate about it. If you're passionate about it, you're going to do something good. The passion is what's more important. And another thing, I believe you are already doing it here, collaboration, partnership with companies or organizations around you. It could be a company, it could be a farming community, it could be dairy farm, doesn't matter. I think here is an opportunity. I think you students, when you go to your town, your village, there's a shop there, or there's an industry there small. Ask them, what do you want, If I have to do something, if there's a miracle, I'm going to make something for you. What do you really want? So asking the customer what you want is a wonderful thing, because that's one way you can do something what they want. Otherwise, what happens that half the things I made in my life that nobody wanted it. So I did work on a startup company, I forgot it. 3 years, $150 million, built a product, nobody wanted it. That was it. So why? Because too much ego, 3 or 13 of us. Too much ego, we think that's what you want. Finally, when we made it, they said, no, I don't want it. So we should ask what you want. Ask your customer what you want. And I think you can do that one. You can do this as a group of students, not just physics, chemistry, engineering. Get some art students with it and ask, go somewhere just for fun and ask a company, just visit them. What can you do to make something better? And bring back to your organization, your university. Well, this is something. What is going to cost making it? That's why you build projects, startup companies. That's how you do it. Figure out what somebody wants and look for money. Never, don't look for the money and then figure it out. That's the worst thing you can do. Figure out what somebody wants and then say, can I make it? Or can I find ways to make it? Can I find resources to make it? There are new opportunities. In the United States, for example, the electric cars to 2021, is about 700,000. Worldwide is almost 7 million. In India, this is 2021, about 330,000. So these are the opportunities: electric cars, design, manufacturing, artificial intelligence, AI. It can be used, self-driving cars, self-driving trucks, robotics. In hospitals, now robotic surgery. So there's a lot of new opportunities, not just one. And I think I have 7 minutes for one. Opportunity in the private sector and public sector. Give an example of, I'm a proponent of private sectors. I'm going to give an example of the company I know quite well, Boeing. The Boeing built a spaceship for NASA. We can take 24 astronauts to space. Each astronaut will cost about $180 million. SpaceX, Elon Musk, we talked about taking risk and building something new, something different. He can put 56 astronauts, $88 million. In other words, the government of the United States is paying twice for Boeing, which SpaceX can do half its price. When I looked at it, I talked to somebody in ISRO. I said, well, we are also doing something similar. The Skyroot Aerospace started in Telangana 2018, and they are doing something similar to SpaceX. In space, a newer company built last year, and that is part of the Department of Space in Ahmedabad. So it's somewhat similar to SpaceX. So there's an opportunity. It means that you have opportunities around you. Go for it. I'm going to recap. Successful innovations comes from lessons, from failures, and successes. Not just yours, others as well. Do your best and enjoy. Means the worst thing you can do that, take a job and do it and hate it. It happens a lot, all over the world. Do something you love. Maybe you don't get as much money you wanted, but you may get enough money you need. There's a difference between want and need, right? There's a big difference. A friend of mine asked me, why don't I buy an Audi A6? Because a lot of people coming from the United States come here, or at least show or tell they have an Audi. I said, so what? What do I do with it? He said, my image will go up. I said, I'm 5'3". How far it can go? It's not going to go anywhere, is it? No. So I never bought the Audi car. And this is an important thing. Ignore what others think. We are all caught up with something. We want to live because what somebody else thinks. Don't worry about it. Don't worry about the Western press. Don't worry about the Indian intellectuals wanting to tell you to do something. No. Don't even worry about your next door neighbor, not your mouse even. Don't worry about it. Do what you want to do. And I think all Indians need to work together to provide quality education. I think it's an important thing for our national progress, national stability, and safety. And these are my closing remarks. My best wishes to all of you students and staff and the administrators. And universities and schools, college have a challenge. You need to focus on quality education. We can have a separate discussion on it. I encourage the university to include opportunities, problem solving, Don't worry about, you need to learn. Okay, you may know quantum mechanics, you know classical mechanics. Can you solve the problem? Say, for example, that, the pipe broke in your house. Water pipes, the one, worst can happen in the toilet. That little thing coming out of it, boom, it broke. What do? You're stuck on the toilet, your pipe broken. What do? For God's sake, you need to learn to fix small things first, right? You start fixing things. Electricity, the switch doesn't work. Make sure that you can fix the toy. You doesn't have to be a physics engineer. You can do it. I did it. And most importantly, anticipate failures. Murphy's law is going to fail. Be proactive. I'm going to expect failure. If you expect something going to go wrong, you can fix it easily. If you have no expectation, you'll never be able to fix it. And the proactive thought process that you can fix it, things might fail or will fail, is important for your education, important for your career, and most importantly, important for your life. Because ultimately, that's what you want, right? Your life. Education is what's important. Education, career, or life, right? There you go. You got the answer. I know somebody's shaking your head, right? You got the answer. I think I'm going to conclude my talk. Thank you. Well, that sounds better than the Uber driver. I like it. Appreciate it. Jai Hind. I'm willing to answer if I can. Thank you very much. Thank you very much for staying. Thank you very much for enjoying at least part of it. I was told by this young lady that since it's in YouTube, no one asks any question. The moment is YouTube is cut off, everyone has questions that one. So assume the YouTube is cut off, because I know some people are listening to it. One of it, my own roommate in NCL, Dr. Yashwant Vankar, and his wife is sitting here, and I suppose he's listening to it too, right? Yeah. And many other friends around